future. We'd like to plug in a diameter and have whatever model we come up with the best prediction possible for the number of serial kernels that could fit on that particular lid. All right, the first thing that you need to do is, here's our data. Let's go see if a straight line is a good prediction model or not. Okay, so what should be on your paper? First thing we do is we check out the linear fit. The slope of the line that best fits that data is around -160. I'm sorry, the y-intercept, and the slope is around 22.5. But the r and r squared just jump out at me. Your r value, 0.9840, that's a very strong, positive linear relationship, wherein 97% of the variation is explained by the least squared regression line, predicting number of kernels based on diameter of the cap. So far so good. Right now a line is an outstanding predictor model. All right, let's go a little deeper. Let's go find our residuals. Remember, the residuals are how far away our prediction model is, our straight line is, from the actual data that we got from this experiment. Okay, to do that, let's go calculate our residuals. Remember, residual is the actual data, the actual response, minus what our predicted would be. So that's L2 minus, don't forget parentheses, paste bars, statistics equation, get to put L1 in there, and these are all of our errors, our residuals. Now there's two things we want to analyze here. Number one is a residual plot. We're looking for a good random scatter, and we want to know how big these errors are. And is that acceptable in your predicting of number of serials that will get on the diameter of this thing? So the residual plot, we'll take a look at L1, L3. We'll compare the explanatory against the residuals, and that's pretty good. Looking for a good random scatter. We don't want some parabola shape. We don't want errors getting bigger. So far so great. All right, let's go calculate our standard error now. This is all written up here now in your analysis. So on number 11, this is what many of you did not do. You did not fit the line to the original points like I asked you to. All right, so now let's take a look at the standard error. In other words, we take all those errors. We know they add up to 0. So we'll square them and add them up, divide it by 7, take the square root. So I'll do a 1-bar stat on the residuals. We end up getting a total variation of 1,288.75. Divide that by 7, and then square root it, and what you guys get, around 16 something? 13.6. Okay, this is going to be an important number here for us in a second. What do you guys think of 13.6? It's kind of big. Now remember what you're looking at here. These are the response variables. Our line is going to make a prediction. Usually it's off, typically, by about 13.6 from these numbers. 13.6 difference in 79 is a pretty big difference. 13.6 from 300, maybe not as big, but this is a pretty, I think, a pretty significant difference. I would like to come up with a prediction model that maybe I wasn't off so much when I was doing my predicting. Okay? So this is a weird one. I mean, R and R squared were great. Residual plot was great, but I think the errors are a bit high. Let's see if we can do better. So what I asked you to work on was to go with the exponential model. Now let's review what we talked about on Thursday. Now the linear model, remember, is you just keep adding a constant. You're adding the slope each time. Okay? That's what the linear model is. Now the exponential model is different in that with each new response variable you keep multiplying by that same constant. Okay, where you see the numbers get really big or really small if you have a fraction here as you go through. But you keep multiplying instead of keep adding by the same constant. That's what the exponential model is. Now the problems that we did before, the original data had this nice curve to it. I don't know, there might have been a tiny curve here. But what we did, this is the big strategy here now. Remember, for May 10th, you have to know 2 transformations backwards and forwards. What do I mean by backwards and forwards? That's all this transformation stuff and all that crazy math we're doing to get the equation. You got to know this stuff for 2 types of problems. An exponential type regression and a power type regression, which is what we're going to talk about today. Now there are hundreds and millions of other types of models that we can come up with. In this class, you've got to know these 2 backwards and forwards. Okay. All right, so remember what we did on Thursday with the exponential model. Our goal is to take that original data and make some sort of transformation to it that will create a straight line. And our trick is, the better that straight line is, then the better our new prediction model is going to be when we do that crazy math to get it back to the exponential. So, what we do in exponential is we take the logarithm of the response variables. We're going to take the logs of all these guys and see what it does for us. Okay, so this is the middle part. Okay, this is what, and a lot of you did a good job in your homework. You just redid the board. You showed all the linearizing, you showed the transformation, all transformation work, and then you showed your math over here. I think that's not a bad strategy as you're going through this. All right, so let's go ahead and go in here. I can get rid of these residuals. They're done now. The line's no good, or at least that's too big residuals for us. All right, so for the exponential model, I'm going to take the log of the response variable. And notice they do get calmed down quite a bit. So let's draw this graph. It's L1, L3. I think that's still the one I'm doing. Double check. Yeah, L1, L3. So let's draw the graph of this one. Now this is the answer to your question. How would I label this? Yeah, this is now the explanatory variable still. This is still the diameter, but this is now the log of the number of series pieces. Okay. Well, I don't know. Doesn't look all that great. Maybe it's a little better. I don't know. So eyeball, I'm not sure I did that much better. But let's go do the test and see how much better we did. So we're going to do a linear regression on our transformed data. And here's what we got. Our R value, 0.9846. What was our last one? 0.9840. I think was our last R value from the original data. This is what we're looking at. If we did better, then ultimately this model is going to be better than the linear was. Did we technically do better? Yeah, we did. Do I expect this model to be a ton better than the original? Probably not. But it'll probably be a little better. Okay, there's R squared. That's a little better. Now don't forget what this is now. We've got our transformed data. This was the log of y, and this was x. We had a bunch of points. The line that fit those points has this equation. Y hat is equal to 1.287 plus 0.061x. So that's the line that fit my transformed data. There's my R, there's my R squared. Yeah.
You want that written on the graph? Right?
Yeah, that's not a bad idea. We're going to use it over here in a second. Last, we need to check a couple more things out. Let's do a residual plot now on this transformed graph. Most of you did a good job on that last night, even if you didn't check out the first one. All right, so to do that, I'm going to take my transformed data, L3, minus parentheses. Let's paste that in there. We did, thank you. I've not been doing that all day. And there are my new residuals from my transformed graph. Now, they're a lot smaller than the residuals I got from the straight line, but I expect that because look what I did to response variables. I made them small by taking a logarithm. So we're still going to calculate standard error, and we're still going to look at the residual plot. Okay, so the residual plot for this one is L1, L4. Still good. Got a good residual plot there written in the line. Got a good residual plot on this as well, so that's fine. Standard error. Let's go take a look at those residuals. They're in my L4. I'll do a one-bar stat on the L4. Okay, that's the variation. So 0.0092 divided by 7. Square root of that, and what does that come out to about?
0.036.
0.36? I expect that to be much lower. I don't want to compare those two numbers because I took logarithms, but that's still of interest to me. We'll see in a second. All right, now, let's go back to the original data. Okay, now I want the original curve. This is how I'm going to get to the equation that gives me my model for the original data. And remember how we do that? We rewrite this as the log of y, because that's really what we've done here, is equal to 1.287 plus 0.061x. That is a curve. The graph of that is the curve, the exponential curve. Now let's write it in different ways. One of the ways we can write it is like this. We write it no longer in logarithm form, we put it in exponential form. So this is y. Now, a lot of you put y hat here. Don't. Y hat's a straight line. This is not a straight line. We'll show it in a second. It's going to be a curve. Okay, 10 to the 1.287 plus 0.061x. This is what I want you to put in your calculator. We'll do it in a second. This is what I want you plugging 17 into. Number 6 last night. Didn't you get some crazy negative number here, like negative 1,000? And when you tried to go get the equation in the right form, it came out to 0. Okay? If you don't leave it in this form, that can happen. It's not really 0, but it's just so small your calculator can't even tell you what it is. Your calculator just says that's 0. Okay, so this is why we work off of this one. Alright, so how do I get that into my calculator? I'm going to go into y equals. We're going to paste it in here. That's exactly what I want to paste into there. So 10 to the, now let's paste it, vars, statistics, equation, and it's gone, so I got to go redo it. L1, comma L3. And now it'd be in my memory. It is, close it off. Now another reason why I like to put it in there is it keeps all those digits for me. Now we can look at the graph of the original data, L1, L2. That's the graph that's going to fit my original point. And that's what I want to see here. I want you to draw that. Yes?
My line's not.
All right, so is that better than the straight line? I don't know. How can we tell? Now, this is a new thing for today. How can we tell if this is any better or not? Now, we know from the R it should be a little bit better. But what's one way that we can determine that? Well, let's go find our new standard error. How much are the predictions missing typically on our curve versus our line? We can do that. We can find the standard error for our curve. And I hope it's lower than 13.6. So let's do that. Let's go in and find the residuals. Let's put them in L5. Okay, now this is from the original line. This is the original X and Y. This is an L1, L2. Okay, and I got these points, and I've got a curve now on them, and I'm trying to figure out those distances. So help me out. What do you think? What do I put? Yes? L2, right? This is the original data. I'm trying to figure out the errors from the original data. Minus
parentheses.
and then...
Oh, and then your equation of line. Then
Equation of the what?
equation of the curve.
Curve. Right there. Isn't that the equation of that curve? So let's put that guy right in here. Okay, 10 to the... Alright, vars, statistics, equation. Oh, good, it was still there. Here, this is L1. Parentheses. Alright, well, how big are those guys? Alright, let's do a one bar stat on L5. That looks pretty similar. Put that, so it's that divided by 7 square root. Somebody give me a number on that. 13.24. So was it better than the straight line? Was it a lot better than the straight line? Did we expect it to be a lot better? Not really. Because why? Because of that r and r squared we had in the middle. All right, that was last night. Questions?
So how do you assess if the standard error value is too high? Because if you're just talking about it in proportion to the actual data, it only has a mean proportion of 0.1.
What do you mean by mean proportion?
Well, I just did like 13.6 divided by all the actual values and then took the mean of it.
Yeah, that's a fancy name of statistics too. Coefficient of something. Yeah, I've learned it back a long time ago. I think what you're saying is you compared that error to these numbers, and what's a good number, what's a bad number. I don't even know. I did that study that at one time. There is an acceptable range in there, and there isn't. So right now we're just kind of doing it by feel. Okay. So right now I thought 13.6 looking at these numbers was a bit big. Okay. 13.424 is still a little bit bigger. Right now what we're doing is can we do better? That's all we're saying. Is can we find a model that will give us lower errors in general? That's what we're trying to do. So I don't know. I'll look that up maybe. Okay, other questions? This is what last night was. This is what I should have seen on your paper. The original data, all the linear analysis of it. The transform data, all the analysis of that. Then going back and plugging in a number. So actually, this is in our y equals. So if we went into table and plugged in 17, there's our prediction, 215.21. And so on your paper, I'd like you to plug 17 right in there. Show me that's where you're plugging it in. And then you've got 215.21 as your prediction for this particular model. Although we don't have as much, hardly any more faith in this than we had for the original straight line prediction. Yeah?
What did we do when we split it up into y equals 10 to the 1.28 plus 10 to the point?
Yeah, that's what we're going to do right now. We're going to do that right now. Okay, but up to this point, I would plug 17 right into this. All right, so what was the math that got it into the actual correct exponential form? All right, remember the first part of the math dealt with this. Whenever you have an exponent, with an exponent with two things added up, I can create just two different exponents multiplied with each other with that same base. So that's what we're going to do right here. So y equals 10 to the 1.287 times 10 to the 0.061x. Then this is a. So let me throw that in there. 10 to the 1.287. Okay, that's the numerical coefficient. This is the base, what we keep multiplying by every time. So what is 10 to the 0.061?
1.15.
So that is the equation in the correct form. But here's something I need you guys to understand. This is the same as this, is the same as this, is the same as this. They're all the same, just written different ways.
So if we ever have a value like we did on the homework where
Just
it
leave.
just goes to 0.
Yeah, right there on your homework. This was like the negative 1,006. Just leave that right there, 10 to the negative 1,000. Okay? All right. That's what we should have walked in here knowing today. All right, the line, I think standard error is a bit high. Everything else looked good. Exponential was a wee bit better. Is there a better model yet still that might work for this? All right, the other model that we need to really understand backwards and forwards is called this power model. Okay, a power transformation. It's similar to exponential. Okay, this is the general form of the power model. And the only thing that's different is that the base and the numerical value switch spots. Let me show you what I mean. And don't worry about writing all this stuff. This is the math stuff we're going to talk about later, so don't write this down. But here's the difference between the three. Remember linear model? It was adding a constant to each one. Exponential model, you kept multiplying by that same constant. In a power model, the power stays the same, and what increases or decreases is the base. When do we use power models? If this was squared all the time, it's like when you're finding the area of something. If this is cubed all the time, it's like trying to find the volume of something. Okay, so that's kind of what the power models are used for. Okay? All right. What's different about the power model? If we think this could be the right model, is you take the log of both of them. Did you do a problem last night where the original data kind of looked like this? But then when you took the transformation, didn't you like overcook the y's a little bit? Does anybody remember that one? That might have been number 11. And it's like, wow, you got patterns in your residual plot again, all over again. That problem last night was actually better fit for the power model. Notice what the power model does. It calms down the response variable, but it also calms down the explanatory variables as well. So this one overcooked the response variable, but if I calm the x's down too, it makes a straight line. Okay? So number 11 was a better fit for the power model than it was exponential. And a lot of you came in this morning and said, I got a residual plot with a pattern in it. My answer was, yeah. Look at your R squared. Is it better? Yeah. But could there be a better model out there? Yeah, that's what it's telling me. All right, we're going to go through the same process now. Except this time, we're going to use the power model. So let's go. All right, clean out all your junk. I don't need any of this stuff now. All right, so I'm going to blow some of you away here. Okay, we're going to go pretty fast with these calculator strokes, so stay as best you can and go watch the tape if you need to. All right, so the power model is we're not only going to take the log of the response, we're going to take the log of the explanatory. So we're going to put them here in L3 and L4. So let's do that. In L3, I'm going to take the log of the L1s. I'm going to really calm those guys down, right? And in L4, I'm going to have the log of the L2s. All right, now let's go through this step now. Let's see how we did. Did we linearize it? Is it better or not from the straight line? Is it better from the exponential? So I'm going to do stat, calculate. I'm going to fit a line. This time it's to L3 and L4. Alright, here's where my eyes go first. Did this improve? What was the other one? 9, 8, what was the other, 4? So, I mean, it's not earth-shattering. There may be other better stuff out there, but when you're this close to 1, I mean, anything's an improvement. So, yeah.
What was your L3 and L4? I was busy re-inputting.
I'm taking the log of the L1s and L2s.
Okay.
So the L3 is the log of the L1s, and L4 is log of the L2. All right, so let's go do our analysis on this. Our graph looks like this now. You gotta get your y equal cleaned up. All right. It's a little more linear, I guess. Not too much, but it's a little bit better straight line. We saw that the R value was 0.987 was better. The R squared was a little bit better. So right now I know that standard error is going to improve. It's going to be a little bit better fit than the other ones were. That's what I know right now. All right, let's go find the standard error and do the residual plot as well. All right, so let's go to L5, and I'm going to find the residuals. So everybody understand what we got here? We got this. This was the log of the x, the log of the y. I've got my points, and I fit a line to it. What was the equation of that line? I want to see that again. So the equation to this is y hat is equal to negative 0.125 plus 2.00x. R was 0.987. That's an improvement, and R squared was also a slight improvement. let's go look at our residual plot and our standard error. So let's go find some residuals. So we're finding the residuals from the transform data. I'm finding this little distance here. So it's L4 minus parentheses, and paste that line in there if it's still in my memory. It is, good. And then what do I put here? What do you think?
I'm sorry, L3.
I agree, L3, right? This is the log of x. This is what created this line, so it would be L3. I agree. There are my tiny residuals again, like I got tiny residuals on the exponential because I'm taking them from logarithms. But let's go ahead and find the standard error for those. So I'll do a calculate on L5. And I remember the last one was 0.009. This is 0.007, so I am going to have a lower standard error. Divide that by 7. Take the square root of it. And it'll be slightly lower than that one we got when we did exponential. So the standard error is going to be slightly lower. Did I get that yet? 0.032. Okay, and that's a little bit lower than the one we got from exponential. Yeah.
How did you calculate L5 again?
Okay, these are the residuals from our transform data. Okay, so it's L4 minus, paste the line, L3. It's the errors from our transformed graph. All right, let's do a residual plot on this, L3, L5, I guess, just to make sure we don't have any pattern all of a sudden. And we don't. Nothing but solid residual plots all the way down the road. So let's now go to the original graph. Okay, we're back to our diameter. So I got that little bit, curve going here, thing I had. So what is going to be the equation that fits that original data? So remember, here was the equation that fit the transform, and we did the same thing we did before. So it's going to be log of y is equal to negative 0.125 plus 2.00 log of x. Yes, because we took the log of both. That's the equation of our curve. That's a power model right there. Let's write it in a form we're a little more comfortable with. So let's take it out of logarithm form, put it into exponent form. So y, the actual number of serial pieces, is going to be equal to 10 to the negative 0.125 plus 2.00 log of x. Let's put that guy in our calculator. Okay, that's the guy we want to plug stuff into. We want to keep all the significant digits in our editor. All right, so we got to get that thing in there right. So it's 10 to the. Okay, now I want to paste that equation. So vars, statistics, equation, and mine's gone again. Okay, it doesn't stay in my memory very long, so I got to go back and redo the L3, L4 line. The transform data line. There's that equation. I got my negative 1.25 and so on. Now I can go back into my editor. Vars, statistics, equation. And now I got a little work to do here. Is it perfectly set up now the way I want it? Look at what we've got written over there. Is that what we have here? What do I need to insert there? Log of x, yes. And I need 2 parentheses now. You know why I like that? It keeps all those digits in there. All right, now if I want to go back to my original graph, the L1, L2, that's the equation that's going to fit the original graph. guys think? Comparing it to the exponential one. Think it looks better? I think it does. Now how can we check? Let's go find out standard error. Let's go figure out how much, on average, typically, it misses in the response variable. Let's go figure out the standard. I hope it's less than 13.6. I hope it's less than 13.4. Let's see. All right, this is tricky now. We're going to go all the way over to L6 for this. All right, now, what are we going to do? How do we do this? It's back to the original data. Go ahead. What do you got? It's L something.
Is it L4?
No! We're back to the original data!
Oh, L2.
Yes! Right? This is the original graph. These are the original numbers. I want to know how much I'm missing. This is my real guesses now. This is what I'm going to try to predict the future with. I'm going on television. I'm going to say, give me a diameter. Okay, I'm going to give you how many cereal pieces I can put on there. I'm not going to give log of cereal pieces, right? I want to know how much I'm off in real numbers. L2 minus parentheses, and now what do I put here? Right there! That's what I want to put. Okay, so let's see if we can get that thing copied in there. 10 to the vars, statistics, equation. Yes, thank you. All right, now we got some weirdness here. What do I put here? You've got two options, and they're both right. Except you probably give me the wrong one. What do we put here now? This is the confusing part. This is what do you got? Reese. What's that?
L1.
No. You had two options and you went yeah.
Log of L4.
No!
Well, log of L1.
What do you got?
Log of L1.
Okay, good. That's one of them that works. Right? This is the equation, right? Where are the x's? Aren't those in L1? So you could do log of L1 or L3. Isn't that where the log of the L1s are? If you guys get confused, just go to this, okay? Just look at this. This is what we're trying to enter into our calculator right now. The y's and x's are our original y's and x's. Those are in L1, L2. So you got two options, okay? You can do the log of L1, or you can just do L3, because that's where the log of the L1s are. I'm just going to stay with log of L1. I want it to look just like that. But you can do the other. You guys are going to do L3 because it saves you 1 second. Two parentheses. And there are our new errors. Okay. All right, so let's just do a one bar stat on L6 to see how big they are. Remember, this guy was 1,228 before, so it's lower, isn't it? So divide that by 7, then take the square root. And what do we get? Is it 8 point something? 8.7? You guys were right. I mean, it did hit those points better. So now I'm going to give you a prediction on how much cereal is going to fit on there, and I'm only going to be off by about 9. Not the best. Maybe there's even a better model than these. Okay? But it's better than the line, and it's also better than exponential. Yeah?
So let's say to answer the warm-up in the power equation, we plug in 17 into...
Yeah, so I'm plugging it right here. 17 right there. Now, it's in my y equals, so if you go to table for 17, that's going to be your prediction. So what does it say in my table right now for 17? So this guy, 217.16, I think that's going to be closer to reality than either one of the other ones. Yeah.
Back to the equation of the curve. Well, it was line. What lines was it for the most previous one?
Say it again.
What it was line. What for L for the equation? Yeah. What lines were those? Like L1.
Well, how did I get this equation?
Yeah.
That equation came from doing a linear regression on L3, L4. That's the equation of that line. Now we put the logarithms in to get it back to the original data. Yeah.
you were assessing the fit of the exponential regression or whatever, which standard error do we use? The one for the transform graph or the one once you fit the...
Once I'm done, I'm interested in comparing these two standard errors. That's the most important, right? That's what a straight line is going to be compared to my curve. Now, when I was in the middle, when I was comparing exponential versus power, this guy's champion. You look at R, okay? If the R is better, that's going to be the winner. But you also notice that the standard errors fell in the line too. So you would compare these two standard errors together, okay? But these are the big standard errors that you want to compare. This is just for comparison purposes against the log of the lines. But this is the big guy. Okay, last step now. So we plug 17 in right there and get that answer. Now what's the math that gets us to this final form of the power model? Well, the first step is going to be just like the one before. Okay, so let's break it into the two tens. So y is equal to 10 to the negative 1.25 times 10 to the 2.00 log of x. Okay, so far, that's just what we did before. All right, this math is in your book. In fact, go to it right now. I want you to take a look at something. I'm on page 216. All right, this was checking out the length and width of rockfish in the Atlantic Ocean. So we're trying to have the length and can you compare how much it weighs. And you look at your original graph on the next page. There's obviously a curve there. R and R squared are probably good, but residual plot has a pattern. Then when they took the log of both, look how much straightened out it got. And the R was 0.99926 and so on. Okay, take a look at the next page. The residual plot looks great here. It's all transform data. And then that next bit is this math we're going to do right here. Okay, so it's in your book as well. So, it's going to be in your notes, it's going to be in your book. Okay, here's the next steps here. This is still going to be our A. So y is equal to, somebody throw that in there. What is 10 to the negative 0.125? What is it? Okay, so that's our numerical coefficient. Okay, that's the number that's right here. All right, here's where the miracle happens. Okay, and you calculus freaks are going to be fine, but us normal people are going to have trouble with this. This is an identity, one of the ones you learned back in pre-cal and algebra 2. And somebody third period. Yeah, it's the inverse. Like it is. Okay. I mean, take a look at this. If this is 100, what is 10 base for 100? Is that going to be 2? So this becomes 10 squared, which is 100. The bottom line is whatever number you put here is going to end up here. When you have the same bases, whatever number you have here is the answer. Okay, so you got to accept that identity right now. Now take a look at what we've got here. Do you see it there? Is that the same thing that we have here? So all of that just becomes the base of x, and the 2.00 stays on top. Okay. Now you gotta remember, this is the same thing as this. It's the same thing as this. It's the same thing as this. They're all the same thing. They're all the equation of that nice power curve that fits those points. Okay. Questions? Yeah.
So for the final equation, it'll always be the exponent of x will always be what you're multiplying log of x by.
Yeah, that'll be your exponent.